champagne and champagne. So his research interests, as you will see from the presentation, include uncertainty and sensitivity analysis, disorder modeling, model selection and validation, stochastic modeling, machine learning, etc. He is the winner of the best paper of the INS Young Professional Thermodynamic Research Competition in 2017, and he was selected as Russell Head Distinguished Postdoc by the National Lab in 2018. Please join me in welcoming our speaker.
Thank you very much for the nice introduction, Professor Ivanov. Good afternoon, everybody. Welcome to the seminar. The topic for this seminar will be revolving around bridging the gap between model and data. And I will demonstrate that our proposed approach can build an intelligent feedback between the simulation and experimentation. And eventually, it has the potential to solve an endless nuclear grand challenge problem. So here's the outline of my talk. In the first section, I will basically talk about the challenge problem to be addressed and a brief overview of my proposed research. In the following three sections, I'm going to talk about theory and applications for inverse quantification, which was developed over my PhD. And this is action to validation and prediction. The final section, in the final section, I will finish up with some closing remarks. And so now let's get started. So at the beginning, let me ask you a question. How many of you went to the 2017 NS annual meeting in San Francisco? Anyone? Not many? Okay. In that meeting, in a special session, NS announced 9 nuclear grand challenges, and they were selected from nearly 300 suggestions that represent the most urgent issues to be addressed to advance the benefits of nuclear energy for future generations. Examples are, wait, I don't think it's showing properly. This is not the bottom, right? An issue. Okay. Yeah. This is the top, right? It's supposed to be the top. Yeah. 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 Do you have a full screen mode? This is still not right. Do you have other reader? Okay, and then we can proceed with the current setting. It's a PDF. Okay. Oh, okay. Okay, thanks. Okay, so now let's continue. Wait. Now this pointer is not working. Okay, good. So now let's continue. These 9 grand challenges will be the basis for NS policy and the research recommendations for the government. Among the 9 nuclear grand challenges, the one we are particularly interested in is called accelerate utilization of simulation and experimentation. This grand challenge says that we need to integrate simulation and experimentation to improve the modern simulation predictive capabilities. This is necessary to transition nuclear energy system design and licensing from reliance on experiments, which are very expensive, to reliance on modern simulation. And this is particularly true to accelerate the technology readiness of advanced nuclear reactors. The research proposed in this talk will provide a possible solution to this NS nuclear. This diagram shows the comprehensive framework to enhance computer model predictive capabilities. This is a very busy diagram. I will not try to describe every block and every connection. So I will only talk about the most important features of this framework. You can see that in the 3 columns, there are 3 major steps: calibration, validation, and prediction. Also, in the middle row, we have the unknown reality of the quantity of interests. And eventually, we want to get a reliable prediction in the prediction domain of the reality. And that is why all these arrows are finally leading to this block. To accomplish that, we are going to consider 4 different kinds of uncertainties in modeling simulation. The uncertainties from the model, the experiment, the code, and the parameter. In a few words, parameter uncertainty are caused by randomness or lack of knowledge, and experiment uncertainty is caused by the measurement noise. The model uncertainty is caused by incomplete or inaccurate underlying physics or numerical approximation errors. And finally, the code uncertainty is very easy to be confused with model uncertainty. Code uncertainty only exists when you use surrogate models, especially when your computer model is very expensive to run. In the next section, I will give a formal definition to all of these uncertainties. For now, let's look at the 3 major steps. The first step is calibration. In the calibration domain, it's also called inverse UQ domain. And in this domain, we have data. In this domain, we're going to inversely quantify the uncertainties in the input parameters while keeping the model consistent with the data. And also, we're going to learn about the model uncertainty using mathematical or statistical approaches. In the second domain is the validation domain. And also, we also have data. And in this domain, we're going to evaluate the degree of accuracy of the calibrated model with the support of data. And we're going to implement some quantitative validation metrics to measure the degree of accuracy. Finally is the prediction domain, where we have no data, and we have to rely on model prediction to learn about the reality. And in this domain, we propose to integrate the results from calibration and validation to improve the prediction. And such integration, I will show that can combine the information from prior knowledge from the inverse UQ domain, and knowledge from the validation domain. So now let's look at the theory for inverse UQ. What is the inverse UQ and why do we need it? So in our nuclear community, when we talk about uncertainty quantification, most of the time we mean forward UQ, which is the process to propagate uncertainties from the input parameter through the computer model to the output parameter. Forward UQ always starts from input uncertainties, for example, the mean values, standard deviations, distributions, or lower and upper bounds. But this information are not usually known to the users, and this is called the missing input uncertainty information issue. Previously, expert opinion or user self-evaluation have been widely used to provide such information, but they are not rigorous mathematically. They can be very subjective, and it goes at a different direction. Based on the comparison of model prediction and the data, inverse UQ can inversely quantify the uncertainties in the input parameters. So now we have seen the motivation of inverse UQ, which is to address the missing input uncertainty information issue. And we want to develop an answer to infer the uncertainties in the input parameters as an alternative solution to expert opinion. And to do that, we have a few objectives. First, we want to always capture the input uncertainties rather than only determining the best fit point estimates. And also, we want to achieve a comprehensive formulation by incorporating uncertainties from the parameter, experiment, model, and code. Thirdly, we also want to avoid overfitting and finally want to reduce the computational cost. Hopefully, all of these objectives will be clear to you after the next section. And finally, we want to formulate the inverse UQ in a way such that it can be the starting step to bridging the gap between model and data, and eventually as this NS and experimentation. The Bayesian formulation for inverse UQ. Here is the problem definition of inverse UQ. Consider a very general computer model, and ym equals ym x theta. It has 2 types of inputs. X is called the design variables, also called system inputs, controllable variables, or observable variables, and is needed by both the computer model and the physical experiments. Calibration parameter theta is only needed by the computer model, and is also called ancillary variables in literature. Examples of X are initial conditions, boundary conditions, and examples of theta are physical model parameters, tuning parameters, or context-specific constants. And it is theta that are usually subjected to unknown uncertainties, and such uncertainty can be aleatory due to randomness or epistemic due to a lack of knowledge, or a mix of the two. And the goal of the inverse UQ is that given experimental data YE, we want to inversely quantify the uncertainties in theta, and while making YM consistent with YE. And the inverse UQ is built on Bayesian inference. And we start from the simple Bayes rule. In the Bayes rule, we have the prior, which is the p theta. That represents our knowledge about the possible values of theta before observing the data. We also have the posterior, which is the probability of theta conditioned on the data. And that is our updated knowledge about theta after observing the data. Finally, we have the likelihood, which is the probability to observe YE given certain values of theta. In other words, how likely are certain values of theta to be true so we can observe the data YE. That is why it's called the likelihood. And the posterior is the solution to inverse UQ. Prior can be chosen by the user, and it can be from expert opinion. And we need a likelihood function to proceed. To introduce the likelihood function, first, let's look at the model updating equation. To assume at the arbitrary experimental condition X, let's define the unknown reality or the true value of the response as YR, where R stands for reality. So how do we learn about the reality? First, we can do experiments. And then in this process, we will always introduce measurement noise, epsilon. Secondly, we can use computer modeling. Let's define the true but unknown values of theta as theta star. However, even though we know the true value of theta star, computer model prediction is still different with the reality. And the difference is called model discrepancy, or model uncertainty, and it's denoted by delta x. Delta x is caused by missing or incomplete underlying physics, or also maybe numerical approximation errors. And here is my favorite example to illustrate model uncertainty. So consider the computer modeling process as students sitting in the classroom and learn to draw a line. And they cannot observe the line directly, which is the unknown reality. Instead, they only have a well-finished drawing of a line from their teacher, and that is our observation. Some students might have a model with missing or incomplete physics. Can anybody tell me what is missing in this model? Yes, the tail. This line has no tail. And also, somebody might have a model with inaccurate physics. We can see this line does have a tail, but it's a tail from a dog. So that is inaccurate physics. Also, at the lower part of this figure, we have 5 models with different level of model uncertainties. And such uncertainties are mainly from numerical approximation errors. And we can notice that all these 5 models have no missing measured parts, right? But still, we can visually tell which model is better. And a typical example of numerical approximation error in modeling simulation is the insufficient spatial or temporal discretization. Apparently, we can see these 5 lines have different levels of measure refinement. So now I think everybody understands what model uncertainty is and what can cause model uncertainty. Now let's go back to the previous slide. So now we have the reality, the experiment, the model. And now we have, from this relation, we have 2 equations. First, experiment data equals reality plus measurement noise, and the reality equals model plus model uncertainty. We can substitute the second equation into the first one, and we get the model updating equation, which states that experiment data equals model plus model uncertainty plus measurement noise. To move forward, let's assume the measurement noise epsilon is to be IID, zero mean Gaussian. And we move this 2 terms to the left. We have epsilon equals YE minus YM minus delta, which follows a multidimensional Gaussian distribution. We can write the density function for this distribution. We get the likelihood, which is shown in this formula. In this formula, the posterior is proportional to the prior times the likelihood. And we can see that the covariance of the likelihood sigma have 3 parts. The first part is called experiment uncertainty, and is due to measurement noise. The second part is the model uncertainty due to missing or inaccurate physics or numerical approximation errors. The last part is the code uncertainty, also called interpolation uncertainty, and is caused by application of surrogate models. I will give you an example later. So apparently from this formulation on the left, we have the parameter uncertainty, and on the right, we have uncertainty from experiment, from the model, and from the code. And that's why this formulation is very comprehensive. And however, because the model uncertainty is the difference between the reality and your model prediction. If you don't know the reality, how can you know the model uncertainty? That's why we need a lot of data to train or describe this model uncertainty. But when you have no data, you have to ignore it. So ignore all the model uncertainty, we have to remove delta and the sigma bias, and we get this equation. However, ignoring the model uncertainty is equivalent to assuming that your model is perfect. Why is that? Let's look at this equation. Without delta, we have reality equals model prediction. That means we are overconfident in our model prediction, and this can cause overfitting. Overfitting means your computer model is over-calibrated to the selected data, but when it's applied to other conditions, you might have big errors. So now we have to move forward from this equation. We have the posterior PDF, and we can see that it is non-standard and not normalized. To generate samples from this equation, we have from this distribution, we have to use numerical sampling, and we're going to use Markov-Chain Monte Carlo sampling. So here is this diagram shows the general idea of MCMC without introducing the complicated math and the statistics behind it. So MCMC, the general idea of MCMC is to generate samples that follow a probability density which is proportional to the posterior PDF without knowing the normalizing constant. So suppose your unknown true value in the input space is shown by the yellow line, and your model, for simplicity, let's assume your model prediction at this yellow line have a very good agreement with your data, and your data can also have uncertainty. MCMC will take a random walk in the input space. For example, we can have samples at these 3 locations, and we have the corresponding outputs. Recall that we have a comparison of YE and YM in the likelihood function. If your corresponding prediction is far away from the data, your likelihood will be very small, and you have a high probability to reject this sample. And you take many random walks, eventually you get a lot of samples. For example, if you have one input, and this figure shows the sample this figure shows the result of MCMC sampling. On the x-axis is the index of the sample. On the y-axis is the value of the sample. And this is also called the trace plot. From this trace plot, you can fit the posterior distributions for this input parameter. But if you have multiple input parameters, you can take a random walk in all the directions simultaneously. For example, if you have 5 inputs, your MCMC samples will be like this. And if you can fit your posterior distributions, which is shown in this figure. On the diagonal, you have the marginal distributions for each parameter. On the off diagonal, you have the pairwise joint distributions for these parameters. So this is the typical result of inverse UQ. We can see that we can not only get the marginal distribution for each parameter, we can also get their correlations. And that's something we can't get from expert opinion. So this is the general idea of inverse UQ. But we notice a big issue in this diagram because we're going to take many random walks. If your computer model is very expensive and you need to evaluate a computer model at every sample, you just can't. The simulation cost will be very high. So you have to use some kind of a surrogate model or meta model. Meta model is also called surrogate model or response surface or emulator. And it's an approximation of the input-output relation of a computer model. And this diagram shows the general idea to build a meta model. So we start with the algorithm for design of computer experiments. We generate a set of training inputs. We run the computer model at this training input, and we get the training outputs. And then from this training input and the output, and with some numerical learning algorithm, we can build a meta model. And the meta model is also called emulator, which corresponds to simulator, and you usually have very low cost. Once your meta model accuracy is validated, at any untried input, you can simply run your meta model to get the output estimation. So some typical algorithm for the learning algorithm, some typical methods for the learning algorithm are moving least squares, radial basis functions, or stochastic spectral techniques like generalized polynomial expansion, sparse graded stochastic collocation, or techniques that has been used for machine learning like artificial neural network, supported vector machine, or Gaussian process. These are some examples. So in this work, we're going to use Gaussian process as an emulator. So there are very complicated math and derivations behind the Gaussian process, but I think this figure will explain what the Gaussian process does. So suppose you have a true function which is shown by this blue line. And this true function is only known at this green dots, and they are called the training size. Then from the training input and output of the training size, Gaussian process can approximate the true function with this green function, with this green line, and that is called the mean value, because at every input, Gaussian process prediction is a Gaussian distribution. The mean value is on the red line and is shown in this equation. And the dashed dotted line shows the 95% confidence interval, which is 2 sigma for Gaussian distribution. And the variance of mean square error is shown in this formula. So the advantage of using Gaussian process as an emulator is that it always tells you the variance of its prediction, which is called code uncertainty or interpolation uncertainty. And this information will enter sigma code. Also from this figure, we notice some other features of Gaussian process. For example, Gaussian process always goes through the training size. That is why it is called an interpolator. And also, the variance of the prediction at this training size becomes 0, and when you get far away from the training size, your variance becomes large. Finally, when you increase the number of training size, Gaussian process accuracy can be greatly improved. So that's the most fundamental ideas of inverse UQ. Actually, there are more intense statistics behind it. For example, the full Bayesian approach and the modular Bayesian approach. I have put them in the backup slide to save some time and avoid confusion. So now let's look at some interesting applications of inverse UQ. The first application is to Bison code. And we all know Bison is a field performance code. And the phenomena we are interested in is called fission gas release. Fission gas release is a very important and difficult phenomenon to model in field performance modeling. And this figure shows the tunnel created by fission gas migration in a nuclear fuel. Fission gas release can cause swelling in the nuclear fuel, which will promote pellet cladding mechanical interaction. And it can also cause gap pressure buildup and some conductivity degradation in the gap. So however, there are significant inherent uncertainties in fission gas release modeling. For example, the fission gas release model in Bison have 5 input parameters that are only known by expert opinion. And the data we're going to use is called the Riso N3 time series data, and which is shown in the green dots. And the Bison prediction with nominal inputs is this blue line. And we notice there is a big disagreement, especially when the power suddenly drops. So what happened here? So when the power suddenly drops, some fuel rod will crack open and release all the fission gases that were previously held up inside the fuel rod. Many field performance codes cannot capture this phenomena, and that's called missing physics. Bison can capture this phenomena, but only to a much smaller scale, and that's called insufficient physics. So, okay, so this is the problem definition for this application. In this application, the Ym x theta is the Bison code, and Ym is the fission gas release time series. X stands for the operating conditions, and the theta represents the 5 calibration parameters, and they are shown in this table. And we can notice for the last, these are all scale factors, and we can notice that for the last 3 parameters, they have a nominal value of 1, lower bound of 0.1, and upper bound of 10. The lower and upper bound differ by a degree, by a scale of 100. That basically means we know nothing about this parameter, and that's why we need the inverse UQ. But we also have some challenges in this application. First, Bison code is very expensive to run. Even with a decent amount of mesh, and it takes about 2.5 hours for one simulation with 32 processors with INL's HPC machine. Secondly, there are large disagreements in the shape of the data and the Bison simulation. And we know there must be model uncertainty, but we do not have enough data to describe it. So in this application, model uncertainty will not be considered. Finally, time series fission gas release data, they correspond to infinite dimensional outputs. And we definitely need some dimensional reduction. In this work, we're going to use principal component analysis. So this diagram shows the workflow of this application. So we have in the center 2 columns. We have the measurement data. And on the right column is the Bison simulation. And on the 2 rows, we have the fission gas release on the original space, and also fission gas release on the principal component subspace. So we start with generating a set of training size for the 5 parameters. we run Bison at this training size, we get a set of the efficient gas release time series predictions. And then we perform PCA and get the corresponding PC scores for Bison. From these PC scores, we train the GP emulator. However, that means during MC sampling, this GP emulator will also always give you a prediction of the PC scores, which is on the PC subspace. But the data is on the original space. How can you compare this YE and the YM directly? So we have two approaches. The first approach is use inverse or backward PCA to transform these PC scores back to the original space and make comparison of Bison and the data. But there's a huge difficulty in this challenge in this approach, which is MC will never converge. Why is that? Because Bison simulation has a very different shape with the data. That means you can never find any combination of the theta parameters to match Bison and the prediction. So we proposed a new approach, which is option B. In this approach, we project the original fission gas release time series data also to the PC subspace. And we make the comparison on the PC subspace. So this YE and YM are both PC scores. So, but what is the physical meaning of this projection? So to interpret the physical meaning of this projection, let's first reconstruct the data. By reconstructing, I mean you project the data to the PC space, and then you apply the loading matrix from PCA on these PC scores and project it back to the original space. And then we got this black line. This is called the reconstructed data. The reconstructed data is the best we can do on the two constraints. First, it has a shape that is similar with Bison simulations. Secondly, it has the minimum distance with the original fission gas release data. By the minimum distance, I mean the distance between this red line, which is the smooth curve of this measurement data points, and this black line. So they are consistent. So the physical meaning of this option B is that projecting performing inverse UQ on the PC subspace is equivalent to calibrating Bison with respect to the reconstructed time series data. So now we can see that the reconstructed data and the Bison simulation has a similar shape. So now it's possible to find the values of theta that can match Bison and prediction. So this is our results for the posterior of the 5 calibration parameters. As I said, on the diagonal term, we have the marginal distributions. On the off diagonal, we have the pairwise joint distributions. And on the right, we have the updated Bison prediction, which is shown in this red line. And we can see that compared with the blue line, which is based on the prior, the Bison prediction comparison with the data is greatly improved. And also for the computational cost, we generated 100,000 MC samples. And it takes about 7 minutes with one processor using the GP emulator, and which would otherwise take more than 20 years if Bison code is used with 32 processors. And and this GP emulator is only trained with 100 Bison simulations. In other words, we have reduced the computational cost in terms of Bison runs from 100,000 to 100, and that's 3 orders of magnitude in the reduction of simulation time. In another application, we apply this inverse UQ theory to trace. So trace includes multiplication factors for 36 physical model parameters. These parameters are all scale factors, and they are widely known as uncertain, but they are usually ignored or treated or assigned expert opinion in previous UQ study. And the data we're going to use is the BFBT benchmark, which is a full-scale BWR assembly. And we're going to use the steady-state void fraction data. So the steady-state void fraction data are measured at 4 different elevations. And from the bottom to the top, we call them void F1, void F2, 3, and 4. So here is the definition of the problem. In this study, YM X theta is the trace code, and the YM are the void fractions. X stands for the 4 testing conditions, including the initial condition and the boundary conditions. And theta, we perform the dimensional reduction using sensitivity analysis to reduce inputs from 36 to 5, because many of the parameters are not relevant to BFBT. For example, some parameters are related to reflooding and stratified flow. So eventually, we have 5 parameters. And theta represents these 5 uncertainty physical model parameters. And this index is used in trace. And YEX in this study is the BFBT steady-state void fraction data. And for this application, we proposed an improved modular Bayesian approach for inverse UQ. And due to the time limit, I will not explain every detail about this application. If you are interested, you can look at our papers published in Nuclear Engineering and Design. It's a 2-part paper. So here shows the workflow of this application. In this diagram, there are 5 major steps. The first step, we developed a few numerical algorithms for test source allocation, which is the process to separate the raw data for inverse UQ and validation for different purposes. The second step is to train a Gaussian process model for model uncertainty. The third step is train another Gaussian process model for trace code itself. And the step 4 is MC sampling. And the last step is validation of the achieved posteriors. So, in this figure, I compare the YE and the YM minus YM versus delta. As I said, model uncertainty has 2 parts. The first part is delta. The second part is the model uncertainty, which is the uncertainty information matrix, sigma bias. So these 4 sub-figures shows the results for void F1 to void F4. And the blue symbol shows YE minus YM, this part. And the red symbol shows delta. Because I mentioned the Gaussian process prediction at every input is a Gaussian distribution. So the red symbol also have an error bar. So the symbol itself shows the mean value, and the error bar shows the standard deviation. So we compare YE minus YM and delta. There are 3 possibilities. Firstly, delta is close to YE minus YM, and the variance is 0. For example, this point. We can see these 2 symbols overlap, and the error bar is 0. In that case, we have YE minus YM minus delta become 0, and this exponential term become 1. And we have no new information enter sigma bias. So we say this data point is not informative. The second case is that delta is close to YE minus YM, and the variance is non-zero. For example, this point. We can see the 2 symbols overlap, but the error bar is non-zero. So we do have some information enter the matrix, and we say this data is informative. In the last step, we have delta is not close to YE minus YM, and this test data is very informative, and this is true for most data points. So this figure shows the results for inverse UQ. On the left, we have the posterior distributions when model uncertainty is considered. On the right, we have the results when model uncertainty is not considered. In the theory part, I mentioned that when the model uncertainty is not considered, we might have overfitting. And we can see the result on the right. The distributions are more concentrated. This is a potential sign for overfitting. And in our validation step, we did prove that this posterior distribution is overfitted to the inverse UQ data. And also in this application, we have a tremendous reduction in computational cost. And by generating 100,000 MC samples, the GP emulator for trace only takes about 37 minutes. But if we use the trace code itself, it's going to take more than 48 days. And so now we have seen the theory and application for inverse UQ. But inverse UQ is only the starting step of this framework. Due to the time limit, I will not have time to talk about the theory and application of validation and prediction. So in this section, I'm only going to present the most fundamental ideas for validation and prediction. In brief, in the validation domain, we're going to evaluate the degree of accuracy of the calibrated model and with quantitative validation metrics. And finally, in the prediction domain, we're going to integrate results from inverse UQ and the validation to improve the prediction. But how do we do that? First, let's look at the validation. The validation metric we are using is called the Bayesian hypothesis testing. And we calculated the metric value called the Bayes factor. So for a typical hypothesis testing problem, we have H0 as the non-hypothesis and H1 as the alternative hypothesis. Examples of H0 and H1 can be, for example, a model is valid versus invalid. If you have 2 competing models, it can be model A is more valid versus model B is more valid. Finally, it can be more accurate versus calibrated model is more accurate. So for notational convenience, let's define the data validation data as D. So we can write the Bayes formula for these two hypotheses. They are shown here, which is very easy. And then we take the ratio of these two equations. We get the posterior ratio equals the likelihood ratio times the prior ratio. Right? This is very straightforward. And also we know that because we only have two hypotheses, we know the sum of the prior probability equals 1, and the sum of the posterior probability also equals 1. Right? So next, what is the Bayes factor? Bayes factor B is defined as the likelihood ratio. Recall the definition of likelihood. For example, P of D given H naught, it means given the hypothesis H naught is true, how likely are we going to observe the data D? So this Bayes factor essentially compares the data support for H naught and H1, right? And if B is bigger than 1, we accept H naught. And if B is smaller than 1, we reject H naught and accept H1. If B equals 1, that means the data support for these two hypotheses are the same. And how can we connect this with prediction? So first, if we have no prior preferences with these two hypotheses, we can assume they are equally likely. That is, the probability, their prior probability are both equals to half. And this term becomes 1, and this term is B. We replace PH1 conditional on D as 1 minus PH not conditional on D. We get this equation. Then by some manipulation, we get this important equation, which states that H naught hypothesis being true, given the data equals B over B plus 1. And this will be used in the prediction domain. So move forward to the prediction domain. Let's collect all the information we have right now. So we have two models to use. The first one is the uncalibrated model, in which we use the prior distribution for theta. The second one is the calibrated model, in which we use the posterior distribution for theta. And now let's define H naught as the calibrated model being more accurate, and define H1 as the uncalibrated model being more accurate. If we use the first model, we rely everything on the prior knowledge. And if we use the second model, we're going to use the information from the inverse UQ domain. Finally, we also have some information from the validation domain, which is their Bayes factor. So how can we combine all these three information to improve our prediction? And we use this prediction formula. We take a weighted average of these two models, and the weighting factor is the probability that this hypothesis is true. That's a very reasonable choice, right? And then from the results on the previous slide, we have the probability of H naught being true equals B over B plus 1, and the probability of hypothesis H1 being true conditional data equals 1 over B plus 1. This is called the prediction formula. And it essentially integrates knowledge from inverse UQ as in theta posterior, validation as in B, and the prior information as in theta prior. So this is the most important formula of this talk, and that's the takeaway information from this talk. So now we have this prediction formula, but there's still one unresolved issue, which is how to calculate the Bayes factor. So calculation of the Bayes factor, you don't have to understand this right now. It either requires some decomposition and integration of the probability. I think we can skip it for now. And now let's summarize this talk. So in this seminar, I presented inverse UQ to address this meeting uncertainty information issue. And the inverse UQ can inversely quantify the parameter uncertainty while keeping the model consistent with the data. And the inverse UQ can avoid overfitting by explicitly considering the model uncertainty. And number 4 is inverse UQ using meta modeling techniques to greatly reduce the computational cost. And also, inverse UQ, the framework is very general and is applicable to all the physics. And for example, reactor physics, field performance, some hydraulics or coolant chemistry. And also, it's comprehensive in the sense that it accounts for uncertainty from all the major sources in modeling and simulation. Uncertainties from the model, the parameter, the experiment, and the code. Finally, starting from inverse UQ, we propose a comprehensive framework that integrates the results from inverse UQ and the validation to improve modeling. And the proposed framework bridges the gap between models and data and can potentially address this NS nuclear grand challenge on simulation and experimentation. The proposed research can support the design and analysis and eventually accelerate the technology readiness of advanced nuclear reactors. I think at the end, I would like to acknowledge the following grants that supported my PhD and postdoc work. And there are one IRP and one NUP from UIUC and one IRP and another NUP from MIT. And also, I would like to thank my PhD advisor, Professor Thomas Kozlowski from UIUC, and the postdoc advisor, Professor Khrushchev and MIT. This work presented in this seminar was performed in collaboration with them. That's all I have. Thank you for your attention.
Questions, comments?
Yeah.
How much of this theory did you generate?
I would say the formulation from the beginning. Actually, I defined all the major sources of uncertainty. The definition is only by me, and the incorporation of all these uncertainties is the first of its kind. Yeah. But the model updating equation, it was borrowed idea from Bayesian calibration. Yeah. And also the prediction Bayesian hypothesis testing is not new, but how to use it to combine inverse UQ and validation, that's new in the prediction domain. Yeah. Yeah.
So you mentioned a couple of examples when you improve the performance of the code, right? And you mentioned
Yes.
the number.
Yeah.
I don't know if both times, but at least once that, for 100,000 samples.
Yes.
This
Yes.
is the time comparison.
Yes.
So thinking about some my own research, which obviously samples are
Yes.
expensive, right?
Yeah.
So is there a certain guideline for specific problems? How many samples you truly need? I mean, 1 million is better than 100,000, but why 100,000? Where does it come from, right? Why
Yeah.
10?
Yeah. So for MC, I have never seen people using number of samples below 5,000. 5,000 is already quite small.
Okay.
It's usually on the order of tens of thousands.
Okay. So,
Yeah.
what is there sort of low diminishing returns if you wish?
Yeah.
Why
Yeah.
not 1 million, for example?
Maybe not necessarily.
To improve the performance, you can do more, right?
Yes. But it depends on, you need to perform a convergence study for MC sampling. If your sample already converged, there's no need to generate samples. Yeah.
Okay. So this number was
just from experience. Yeah.
Thank you.
Yeah. Any more questions? Yeah.
So you reduce dimension from 36 to 4
Yeah. Yes.
via some linear analysis.
Yes.
How did you decide 5 parameters are enough?
Okay. So I mentioned that there are 36 physical model parameters. For example, some parameter related to heat transfer coefficient, from a single phase or two phase.
Trace allows
Yeah.
you to.
Yes, trace. You can input these values for as the multiplication factor in the input file, and many of the parameters are not related to BFBT. I mentioned stratified flow, reflooding parameters, and for the we use the 2 steps. The first step is global sensitivity using Morris screening or by some perturbation based. That's the local sensitivity. The second step, we calculated the Sobol indices. And actually, I have results in the backup slides. Yeah. Trace. So I have skipped a lot of details in these applications. And that's trace dimension reduction. So we first perform a preliminary local sensitivity analysis, and we identified 8 potentially significant parameters. And then the second step, we calculate their Sobol indices. And we identified 5 parameters that have non-negligible significance. Yeah. Yeah.
So you showed a case for single phases with coefficients.
Yes.
Regressions.
Yes.
And have you ever tried this method for multi-phases, such as the field modeling parameters with the thermal hydraulics? Let's say field conductivity and void transfer.
No, I haven't tried that, but I think that I mentioned the framework is very general. It's just you apply to the different applications as long as you have data. And I think you are trying to mention that what if you have multiple inputs, multiple responses, right? Okay, that's a very good question. And I think for multiple responses, the most important issue is the correlation between these outputs. And you can see, okay, sorry. In this, you can see all this uncertainty, they are matrices. You can put your measurement data correlation, measurement uncertainty correlation into this matrix, and the model uncertainty correlation into this matrix, and code uncertainty correlation into this matrix. If you believe there are no correlations in your responses, just diagonal matrices. Yeah, so it's very flexible.
Other questions?
Any more questions? Yeah.
So we do PCA
Yeah.
to reduce that. PCA on a time series?
Yes. I think I have details. Python PCA. Yes. Yes, this is the results. And yeah. For what is that? Sorry, I didn't catch. Yes, yes. In the actually conversion, you can see that I know it's not readable for the PCA we have. And you can see that there's no big difference with how many samples you use, right? That's the convergence study for PCA. Yeah. That's why we did it in this study.
What about the accuracy of inverse PCA?
But there's so for inverse PCA, I'm not sure if the process is to apply this loading matrix from PCA onto the PC scores, right? So as long as your forward PCA, the number of samples is determined, there's no accuracy convergence study for inverse PCA. Yeah, yeah. Any more questions?
So for this inverse
Yeah.
uncertainty identification,
Yeah.
so if you have data, you have high fidelity,
Yes.
you can use it back to determine
Yes, yes.
in the input parameters.
Yes, you mean the high fidelity?
Yes, in all parameters, so selected parameters.
I believe you have to do a sensitivity analysis first, because inverse UQ we have a paper about the inverse UQ issue called non-identifiability. So identifiability issue means, so this is the model prediction, that's your data, and they are different. But the difference the reason for the difference have three parts: parameter uncertainty, model uncertainty, the model discrepancy, right?
Yes.
Right? So even though you assume the measurement uncertainty is known, you still have two parts. And highly ill-posed, you might have multiple solutions, right? Because many combination of these two terms can result in the same discrepancy. If you do not do a sensitivity study, I just do inverse EQ for all the parameters, some parameter solution, and you cannot convert. Yeah. Yeah.
Last call.
Yeah, sure.
From your posterior distribution,
Yeah.
did you sample the parameters to use in your actual applications, or did you use mod, or if it's perfectly normal, did you use mean?
Okay. So I think you're talking about once you have this posterior distributions, how to use them in your forwarded UQ,
Yeah,
right?
So it's
Yeah.
basically a probability that says that your parameter is
Yeah, sure, you can.
this distribution.
Yeah.
So for example,
Yeah.
in your lower right,
Mhm.
it doesn't follow. If you cannot use mean directly, so
Yeah. So to answer this question first, of course you can fit the posterior distribution with a well understood distribution like a gamma distribution
yeah.
or log normal, right? Or normal distribution. If you do not want to do so, actually empty sampling will simultaneously generate good outputs at these training samples, at these empty samples. You get what I mean? Because empty sampling, the YM is always calculated simultaneously, right? Yeah. More questions?
Okay, let's thank the speaker.
Yeah, thanks.